The topic of the day is field theory. Field theory is a large topic. You started it in grade 11. In fact, if you were in my class taking this in the hybrid model in grade 11, you'll recognize this document. A lot of this first part I just took right out of the grade 11 one as a review. In grade 12, we're going to add on to field theory, add a bit more math to it, make it a little bit more complicated, or since our math is more sophisticated, we can bring our field theory up to match where our math is. And as your math continues to get better and better, then you'll circle back and improve and do a bit more field theory. For example, in university, once you learn a bit more calculus, you'll do calculus on field theory and how all these weird vectors could be changing over time. Um, as usual, we'll take the scenic route. Really, the goal is to get to electric force, electric field, electric energy, and electric potential. We'll take the scenic route to get there. I think it's a good investment of our time because hopefully it'll make the new stuff click a little bit better if we just backtrack and make sure the basics are down pat. So how I like to describe this topic is there's these things called vector fields. So for example, I Google searched this, sorry I didn't cite it properly, but I found this image of map during a typhoon. Even without really knowing the math behind it, I imagine or I hope looking at that thing, you could get a feel for what that's communicating. You could have an idea where the wind was blowing the hardest. You could see where the wind isn't really blowing. You could tell which direction the wind was blowing. You could kind of read this thing even if you don't know what it's all about. For example, in this corner, there doesn't really seem to be any arrows. So that means there's no wind blowing. Up here, there's a lot of arrows. They're jam-packed close together. They're all fairly long, so I think that's where the wind is blowing the strongest. And it's kind of blowing north and east. Down here, the wind is blowing mostly to the west. Over here, it's blowing mostly to the east. So I can kind of read this thing. I can get an idea for where the wind is blowing hard, and I can get an idea for the direction of the wind. That diagram is a vector field, just a map or a distribution of arrows. The length of the arrow, the density of the arrows, the direction of the arrows all communicate something about the vectors. In this case, the vector was the wind velocity. The goal for today, we're going to focus on electric fields, but the goal of this whole unit is to be okay with electric fields and magnetic fields. I'm going to gloss over gravitational fields because, like I said, I think it's an investment that'll pay off. The behind the scenes thing is way back in the late 1800s, physicists weren't happy with how they were explaining these forces that we call action at a distance. Action at a distance are gravity force, electric force, and magnetic force. There wasn't a good answer for the how they worked. We're going to review gravity, but way back in the 200 years earlier, in the 1680s, Newton developed his equation for gravity, the story about the apple falling and hitting him in the head. Even when he came up with it in the 1680s, he didn't like it. Here's a quote here I found on the internet. I use it every year. I think it was translated into English because Newton was kind of weird and liked to write in Latin, and well, Newton was just kind of weird. But the last part here. Basically, he's saying that gravity is this inherent, essential, one body acts upon another at a distance without the mediation of anything else. They're force conveyed from one another. The whole idea of how we framed gravity, so basically this is saying what gravity is in his model. He's saying that if you believe what my model says, that is so great an absurdity, this idea of gravity, that no person who has, in matters, philosophical matters, a competent faculty of thinking can ever fall into it. So basically he was saying you'd have to be a knucklehead. Basically his theory says gravity objects magically attract each other. You'd have to be a knucklehead to believe it. There must be something else to convey. There must be something else to mediate that force. That's what field theory is. Field theory is an invented theory trying to say what's conveying or what's mediating that force. We're going to backtrack and talk about gravity. Again, in grade 11, we learned Newton's gravitational force. We reviewed it in grade 12, right around when we were doing satellite motion. It's the same thing as what we did before, but I want to set up gravity so that electricity clicks a little bit easier. The logic behind gravitational field theory is gravity is all about mass. Any object with mass is surrounded by an invisible gravitational field. The vector field is kind of like the map of the wind. It's a bunch of arrows that describe, in this case, the gravitational force the mass would put on something else. For example, if we think about Earth, Earth is big and heavy, a lot of mass. If another mass were close to Earth, that other mass would be attracted to Earth. So we draw the gravitational field of Earth as a bunch of arrows pointing towards Earth to indicate that another mass would get attracted towards Earth. They're all towards Earth because gravity is always attraction. If we look a little bit closer, kind of close to Earth, the arrows are closer together than they are farther away from Earth. That means that the field is stronger close to Earth than it is farther away from Earth. Newton came up with the equation. The equation still holds. Now we're going to get to Newton's equation second. It matches Newton's work, but basically any object with mass is surrounded by an invisible field. The equation that tells you how strong that field is, it's where we get the 9.8 number. Gravitational field is g, which is our gravitational constant, multiplied by the mass, divided by r squared. And like we saw before, the r is the distance from the center of the object out to the point we're curious about. So the r would measure from the center of Earth to wherever we're measuring to. So anything with mass is surrounded by this invisible gravitational field. Where the force comes from is that if we have two masses and they're close enough together that their gravitational fields overlap, that's what mediates, that's what creates the force. Two fields interacting with each other, they create the force and they store energy. There's no magic anymore. It's the interaction and overlap of fields that creates this force and stores the energy. The equations still work. We saw this equation for Newton's gravity. It's gmm over r squared. We did the cool calculus proof earlier. The equation still works for energy. The gravitational energy has got a negative sign, gmm over r. The negative, we talked about that at length because little m is trapped by big M, a positive work. We get them to move farther apart. All the equations are exactly the same. It's just the logic. The reason for the why there's gravity. Masses create fields, and the fields, their overlap creates the force and stores the energy. I'm going to pause this video. What I'd like you to do is work through the practice question, and then we'll move on to really the meat of this. We're going to start talking about electricity next.